Understood. Here is a rewritten script in one paragraph, preserving the structure, tone, style, and meaning while changing the wording. At this moment, you're convinced that the Andromeda Galaxy sits 2.5 million light-years away from you. You're convinced the closest star lies 4 light-years off. You're convinced that distance across space is genuine, quantifiable, absolute. But suppose every single reading you've ever taken of cosmic separation is mistaken? Suppose distance itself isn't a basic feature of reality, but an illusion your mind conjures? Suppose that at the most fundamental layer of physics, space contains no distances whatsoever? What I'm about to reveal will forever shatter your grasp of what space truly is. Distance seems like the most self-evident thing in existence. You're seated some distance from the screen, showing you this. The moon rests 250,000 miles off. The sun sits 93 million miles away. These separations feel genuine, absolute, unchanging. Distance is simply how far apart things sit. It appears to be the plainest idea in all of physics, yet plainness is frequently the disguise worn by the deepest riddles. And distance, the most seemingly evident quality of space, proves to be among the most deeply misread notions in all of science. Distance across space is not what you imagine it to be. It isn't fundamental. It isn't absolute. It isn't even genuine in the manner your instinct insists it is. And the path to grasping why will carry you through quantum mechanics, general relativity, holography, and the very bedrock of what space itself actually is. Let me begin with something you may assume you already grasp: the speed of light and what it reveals about distance. When astronomers declare the Andromeda Galaxy sits 2.5 million light-years away, they're offering a claim that sounds like a distance reading, but is truly a time reading. A light-year is the span light crosses in 1 year. So declaring something 2.5 million light-years off means light needs 2.5 million years to journey from there to here. But here's the catch. You aren't gauging where Andromeda sits right now. You're gauging where it stood 2.5 million years ago when that light departed. By the time the light lands in your telescope, Andromeda has shifted. It's been moving for 2.5 million years. The distance you record is the distance to a phantom, to where Andromeda once was millions of years back, not where it truly sits at this instant. And owing to the stretching of the universe, the genuine present distance to Andromeda differs from the distance the light crossed to arrive. Space expanded during the 2.5 million years the light was in transit. So the distance the light crossed isn't identical to the current gap between you and Andromeda. Every cosmological distance reading blends together at least 3 separate distance ideas: the distance light crossed, the distance at the moment of departure, and the current distance factoring in expansion. These are all distinct figures. Which one is the real distance? The reply is that none of them holds more reality than the others. They're all legitimate gauges of separation, depending on what you're asking and what reference frame you're applying. There's no single truth of the matter about how far off a distant galaxy sits right now. Distance at cosmological scales is observer-bound and definition-bound. It's not an absolute truth about reality. But this is merely the opening. Special relativity presses much further in dismantling the absoluteness of distance. Einstein revealed in 1905 that distance is relative, not roughly relative or somewhat relative. Absolutely, fundamentally, mathematically relative in a way tied to how quickly you're moving. Here's the central finding. A ruler racing past you at high speed is shorter than an identical ruler standing still. Not because the ruler is physically squeezed, not because something is pressing on it, but because the geometry of space-time is such that a moving object takes up less space along the direction of motion than the same object at rest. This is length contraction, and is a genuine, measured, experimentally verified fact. At 10% of light speed, an object shrinks by roughly 0.5% along the direction of motion, slight yet detectable. At 90% of light speed, it shrinks to about 44% of its rest length. At 99% of light speed, it shrinks to about 14% of its rest length. As you near light speed, length nears zero. What does this signify for cosmic distances? It signifies that distance is frame-bound. If you're aboard a spaceship traveling at 99% of light speed toward Andromeda, the distance from you to Andromeda isn't 2.5 million light-years. It's 2.5 million light-years divided by the Lorentz factor, which at 99% light speed yields a distance of roughly 350,000 light years. You and someone standing still on Earth will record entirely different distances to the same galaxy. Both readings are correct within their own reference frames. There's no absolute distance at the speed of light. The contracted distance would be zero from a photon's viewpoint. If it possessed a viewpoint, which we settled in an earlier video, it does not. The distance from its origin to its target is precisely zero. Every cosmic distance is zero for a photon. The whole observable universe holds zero size from the reference frame of light itself. So distance across space is already not absolute. It hinges on your speed. It hinges on your reference frame. Different observers record different distances between the same 2 points, and every one of their readings is equally valid. There's no truth of the matter about the actual distance between 2 points in space independent of who is measuring it and how they're moving. But even this isn't the deepest layer at which distance falls apart. General relativity presses further. In general relativity, space itself is bent. Mass and energy warp the geometry of space-time. Near a massive body, space is bent considerably. This means the distance between 2 points isn't fixed by some set background geometry. It's fixed by the arrangement of matter and energy between and surrounding those points. Near a black hole, space is so bent that the distance from beyond the event horizon to the singularity within is effectively endless. Even though the black hole holds a finite radius, as gauged from outside, an infalling observer experiences the inside of a black hole as holding tremendous volume. Vastly greater than the black hole appears from outside. The interior of a black hole contains enormous quantities of space unreachable from outside. This reveals that distance isn't a set quality of space. It's fixed by the geometry, which is fixed by matter and energy. Alter the arrangement of matter and energy, and you alter all the distances in the universe. Distance is a stage upon which physics unfolds. It's itself a physical quantity that shifts depending on the physical setup of the universe. Bent space also means the shortest route between 2 points isn't a straight line. In bent space-time, the shortest routes are called geodesics, and they trace the curvature of space. The distance along a geodesic hinges on the curvature, and the curvature hinges on the mass and energy arrangement. 2 points sitting close together in flat space might be far apart along the geodesic if a massive body lies between them, or might seem close together owing to gravitational lensing bending light around the massive body. Even the idea of 2 points sharing the same location turns strange inside a black hole owing to the extreme space-time curvature. 2 points that occupy the same spatial location according to one coordinate system can occupy vastly different locations according to another coordinate system. The coordinates we apply to label points in space-time are arbitrary. Different coordinate selections yield entirely different accounts of which points sit near each other and which sit far apart. This isn't merely a mathematical technicality. Physical effects depend on coordinate selection. What resembles a strong gravitational field in one coordinate system resembles flat empty space in another. What resembles a huge distance in one coordinate system resembles a tiny distance in another. The coordinate invariant truths about space-time concern its geometry and topology, not plain distances between points. Now we arrive at the deepest and most radical way in which distance across space is a mirage. Quantum entanglement and the holographic principle. Quantum entanglement is perhaps the most bizarre phenomenon in all of physics. When two particles interact and grow entangled, they form a single quantum system portrayed by one wave function, no matter how far apart they are later carried. Measure a property of one particle, and you instantly learn the matching property of the other particle, regardless of the gap between them. Einstein branded this spooky action at a distance and spent years striving to prove it impossible. He was mistaken. We verified entanglement in thousands of experiments. Two entangled particles can rest on opposite ends of the observable universe, and they stay one quantum system. Spatial separation doesn't sever entanglement. Distance doesn't dull it. Two entangled particles billions of light years apart are quantum mechanically closer to one another than two unentangled particles that are touching. This reveals something profound. Quantum mechanical nearness and spatial nearness are wholly different things. Two particles can be spatially far, but quantum mechanically linked. Two particles can be spatially side by side, but quantum mechanically separate. Spatial distance fails to capture what's genuinely unfolding at the level of quantum reality. Physicist Juan Meldacena made one of the most revolutionary breakthroughs in the history of theoretical physics. In 1997, he uncovered precise mathematical equivalence called the AD/CFT correspondence between a theory of gravity in a certain curved spacetime and a quantum field theory with no gravity dwelling on the boundary of that spacetime. The gravity theory dwells in a space with one more dimension than the boundary quantum theory. Yet the two accounts are wholly equivalent. Every observable in one theory has a precise translation into an observable in the other theory. They portray exactly the same physical reality from two entirely different vantage points. This is a holographic principle in its most precise mathematical form. The physical reality we encounter in 3 dimensions of space can be wholly and exactly portrayed by a theory dwelling on the 2-dimensional boundaries of that space. The 3rd dimension of depth, the dimension that grants us our sense of depth and distance, isn't fundamental. It's emergent. It springs from the quantum entanglement structure of the boundary theory. Consider what this means for distance. In the 3-dimensional bulk theory, you have distances. Things are near or far apart. Gravitational effects hinge on distance. The geometry of space-time sets distances. All of this appears fundamental and genuine. But in the 2-dimensional boundary theory, there's no bulk distance. The 2-dimensional boundary theory carries its own distances. It's 2-dimensional geometry. But the 3-dimensional depth, the distance into the bulk, isn't a geometric distance in the boundary theory. It matches something entirely different. Specifically, it matches the energy scale of the boundary theory. High energy processes in the boundary theory match small distances from the boundary in the bulk. Low energy processes match large distances from the boundary. What we sense as distance in the 3rd dimension of space is truly energy scale. In the underlying quantum theory, distance isn't fundamental. It's a way of portraying quantum mechanical relationships between degrees of freedom at different energy scales. Depth in space is an emergent quality that springs from the structure of quantum entanglement in the boundary theory. This is an approximation or an analogy. This is an exact mathematical equivalence demonstrated to extraordinary precision. Space, specifically the radial distance dimension in the holographic picture, is literally emergent from quantum entanglement. Recent work by physicists Mark van Ramsdonk, Brian Swingle, and others has rendered this link even more explicit. They've shown that the geometry of space-time, including all its distances and curvatures, is set by the entanglement structure of the underlying quantum fields. Specifically, a concept called entanglement entropy, which gauges how quantum mechanically entangled different regions of a quantum system are, sets the geometry of the matching space-time. Regions of space-time sitting close together match strongly entangled regions in the quantum account. Regions of space-time sitting far apart match weakly entangled regions. Distance across space is entanglement in quantum mechanics. These are 2 accounts of the same underlying reality. Van Ramsdonk illustrated this with a beautiful thought experiment. Take the quantum state of the boundary theory and lower the entanglement between 2 halves of it. What befalls the bulk space-time? The bulk space-time splits into 2 disconnected pieces. As the entanglement is lowered, keep lowering entanglement to 0, and the 2 halves of the bulk space-time grow wholly disconnected with endless distance between them. Restore the entanglement, and the 2 halves rejoin, and the distance shrinks. Space-time connectivity. The fact that different regions of space are linked to one another with finite distances is literally forged by quantum entanglement. Strip away entanglement and space crumbles. Add entanglement and space is sewn together. Distance is an equality that space carries on its own. Distance is an expression of quantum entanglement between the degrees of freedom that make up space. This insight has driven one of the most thrilling recent advances in theoretical physics. The ER equals EPR conjecture put forward by Meldacena and Leonard Susskind themselves. Einstein-Rosen bridges, which are wormholes joining 2 distant regions of space-time, are labeled after Einstein and Rosen, who first described them mathematically. Einstein-Podolsky-Rosen pairs, which are maximally entangled quantum particles, are labeled EPR after the famous 1935 paper by Einstein, Podolsky, and Rosen. The conjecture states that ER equals EPR, that is, An Einstein-Rosen bridge between two black holes is the same as an EPR entanglement between the two black holes. A wormhole joining two distant regions of space is equivalent to maximum quantum entanglement between those regions. The geometric link through a wormhole and the quantum mechanical link through entanglement are the same thing rendered in two different tongues. What does this mean? It means that entangled particles are joined by a kind of quantum wormhole, a geometric bridge through space-time forged by their entanglement. Two particles that seem to be spatially far from each other, because you can't see the quantum bridge between them, are truly geometrically joined through that bridge. The distance between them is a mirage forged by peering at the wrong layer of description. Our ordinary notion of distance, the distance you gauge with a ruler or a laser rangefinder, is the large-scale emergent account. Beneath it, at the quantum level, the real structure is entanglement. Two entangled particles aren't far from each other in any fundamental sense. They're joined. Distance is a macroscopic mirage that arises when you average over quantum details. Loop quantum gravity offers yet another vantage on why distance isn't fundamental. In loop quantum gravity, space-time isn't smooth and continuous at small scales. Instead, it's built from discrete quantum units, tiny chunks of space called spin networks. The nodes of a spin network stand for a quanta of volume. The links between nodes stand for quanta of area. Distances in loop quantum gravity aren't continuous quantities. They're discrete quantize, arriving in minimum units tied to Planck length, which is about 10 to the minus 35 meters. At scales beneath the Planck length, the idea of distance grows meaningless, not merely unmeasurable, meaningless. There's no physical truth about whether two things are parted by less than a Planck length, because spatial separation beneath this scale isn't a meaningful idea. Space isn't endlessly divisible. It carries a smallest unit, and beneath that unit the very notion of distance breaks down. This means our smooth, continuous space with its infinite precision distances is an approximation. It performs extremely well at scales far larger than the Planck length. But it isn't the fundamental reality. Fundamental reality is a discrete quantum network where classical distance springs up as a large-scale statistical quality of a network, the way temperature springs from the average motion of molecules. Even though individual molecules don't carry a temperature, distance across space is therefore doubly illusory. At the quantum gravity scale, space is discrete and distance loses its classical meaning entirely. At larger scales, distance springs up as an approximate account of the underlying quantum network structure. But this emergence means distance isn't fundamental. It's derived. The implications of all this are staggering. Two galaxies that seem parted by millions of light years might be joined by quantum entanglement in ways that render that spatial distance physically irrelevant for quantum processes. The seemingly vast distances between stars might be, at the quantum level, accounts of entanglement structures rather than fundamental gaps in space. The universe that seems to stretch across billions of light years might be, at the deepest level, a quantum system where what counts isn't spatial geometry, but quantum connectivity. This doesn't mean you can instantly teleport across the galaxy by tapping quantum entanglement. Entanglement doesn't permit faster than light communication or transport of matter. The quantum link between entangled particles doesn't forge a traversable tunnel for information or energy. The distance is a mirage at the fundamental level, but the limits on what can physically unfold between distant regions stay firmly in place. You can't tap the underlying quantum connectivity to break causality. But it does mean that our whole picture of the cosmos as a vast, empty space with things scattered across it at enormous distances is fundamentally misleading. The universe isn't primarily a spatial structure. It's primarily a quantum structure. The spatial distances we observe are a macroscopic emergent account of the quantum entanglement architecture of reality. Consider what this means for how you view the night sky. When you gaze up and see the Milky Way stretching across the darkness with stars at distances of hundreds and thousands of light years, you aren't seeing fundamental spatial separations. You're seeing the large-scale average of a quantum entanglement network. The apparent distances are genuine as macroscopic accounts, but they aren't the bottom layer of reality. When you look at the Andromeda Galaxy and ponder the 2.5 million light-year gap between us and it, recall that this distance is frame-bound, observer-bound, definition-bound, and ultimately emerging from quantum entanglement structures that don't themselves speak the language of spatial distance. When cosmologists gauge the scale of the observable universe at 93 billion light-years and describe it as unimaginably vast, recall that this vastness is an account in the approximate language of classical geometry. In the underlying quantum account, there are number 93 billion light-years. There are quantum states and their entanglement patterns, and the geometry, including all those distances, springs from those patterns. Distance across space is genuine the way that temperature is genuine. You can gauge it, you can feel it, you can build technology upon it. But it isn't fundamental the way quantum states are fundamental. It's an emergent, approximate, observer-bound account of something deeper that carries no distances. The universe isn't a gathering of things scattered across a vast space. The universe is a quantum system, and what we call space, with all its distances and geometries, is the way that quantum system appears from within. When you're a macroscopic being made of trillions of atoms interacting at energies far above the quantum gravity scale, you aren't parted from the stars by light years. You're joined to them through a web of quantum entanglement, whose large-scale account we call space. Every particle in your body is quantum mechanically joined to particles throughout the cosmos. The apparent distances between you and everything else are the macroscopic shadow of quantum links that carry no spatial description at the fundamental level. This is what distance across space truly is. Not a fundamental quality of reality. Not an absolute truth about how far things sit from each other, but an emergent, approximate, observer-bound account of quantum entanglement architecture. A handy fiction that we mistake for fundamental reality because we're too large to spot the quantum structure beneath. The universe isn't vast. The universe is quantum, and in the quantum account, there are no distances.